We just wanted to go over number 2 today here in class. And we've got this reaction to where we've got NO plus O2 to give us NO2. Okay? And then the next thing that you would have to do is to balance that. And upon doing so, okay, if we put a 2 here, okay, then we're going to have to put a 2 there. All right. So upon doing so, now we've got our equation balanced, and we're starting with 0.499 liters of that substance, correct? Now this is for number 2. Okay? This is for number 2. All right? Because it says, what mass of oxygen you require to oxidize 499 cubic centimeters or 499 milliliters of NO to NO2. So that means how many grams of this would we need? Okay? So if you are an ideal gas law person, the difference between what we did before, that was, again, composition gas stoichiometry, where you weren't looking for a volume, because that was tied up into this, every mole has 22.4 liters. So this is all the information that you'd have for the ideal gas law. You're starting with almost half a liter, okay? So on the left-hand side of our equation, we have 0.499 equals 22.4 N. And of course, that comes from multiplying these two numbers, okay? There's our constant of 22.4. So when we divide each side by 22.4, okay, that gives us 0.02 moles of nitrous oxide, okay? Now this is if you're doing the ideal gas law. You take that substance then, okay, now you're in familiar territory with what we did in chapter 9. Because you could take this now, 0.02 moles of NO, and how do we get that to grams of oxygen now? How do we cancel out this mole of NO? Okay, we put moles of NO, and that's for every mole of O2. Okay, we've got a mole-to-mole ratio, which means you have to go back to your reaction. So we have to put a 2 into there, which means we put a 2 here. Okay, these moles have canceled. And this is where that practice of carrying that 2 every time will help you out, because for every mole of O2, how many grams do you have? 32. So then when you multiply this number, or you just use the dimensional analysis, it's 2 different ways of solving the exact same problem. This is if you're dimensional analysis, or excuse me, this is if you're the ideal gas law. This is if you're straight out dimensional analysis, because it's at STP. To me, the likelihood of making a mistake is less when you do this, straight up dimensional analysis. But if you want to use the ideal gas law, you certainly can. You just have to solve for the moles of the substance that you have, which was NO, okay? And that's what we did here. So once you get that into the number of moles that you have in the ideal gas law right here, then we're back to that familiar territory. You put that into moles, cancel that out with moles of O2, and change that to grams. And I think you get like 0.36 for one of these and 0.32 for the other. But I think for this, I just multiplied by 44, and that's probably why I'm off just a little bit. But again, choose which one you want to be if it's at STP. If it's not at STP, then you have to use this ideal gas law. All right, so hopefully that gets away from any of the confusion that we've had for number 2. Is there anything else that you'd like to add while I have this rolling? Otherwise, we'll just say the rest of the time then is yours. Going once, going twice, you say sold. All right, we'll catch up to you next time.